So next we have Nguyen Quynh and Tim Wooten of Smith Interconnect in Milpitas. So Quynh is a mechanical engineer since 2014 at Smith's. She holds a bachelor's in mechanical engineering from San Jose State University, majoring in mechanical design and minoring in thermal. She has more than 15 years of mechanical design and thermal management experience in the semiconductor industry. Tim has been a product line manager for 2 years. He's an expert in semiconductor package test with deep experience in the design, deployment, and application of advanced test socket solutions. These are used at system level test, RF testing, POP, SOC, high power, thermal, and fine pitch. He has a specific expertise in technical sales, product development, marketing, and business development. Please go ahead.
Thank you. Quynh and I are both honored to be nominated as two of the hottest people in the industry. We're really grateful. I thought we were going to accept an award today, but we'll actually do a thermal presentation. And Quynh?
Thank you, Tim and Rob. So today I'm gonna discuss about the thermal management for the IC system level testing with the manual mode. Advance in the high-end floating point processing, machine learning, and AI have led to a new class of device that demand performance at all time, and then at all power cost. As a result, extreme high gate count device are being designed that have incredibly high power draw. So as you can see, around 2016, the majority of the IC monolithic, and it can dissipate to around 50 to 90 watts with the bandwidth of around 20 to 30 gigabits per second. Within a year or so, then we can see a lot of MCM architecture IC that can generate up to 150 to 200 watts with the memory, the bandwidth increased to around 80 gigabit per second. So nowadays, we see mostly the chiplet architecture with the large die in the center, which have most power, and then some high bandwidth memory in the on the side. This chiplet we've seen so far around 250 watts, and it can go up to 350 watts. And currently, I've seen design requirement for around 600 watts to 650 watts. So today, I'm gonna discuss some of the thermal management for testing this high device and the advantage and disadvantage in the manual test setup. So I know that we are all familiar with the test setup for the IC chip. Let us go over it briefly just for the purpose of this presentation. So for this one, we mainly discuss about the manual test setup. So so far, since Tuesday, we heard a lot about auto tests and all that, but there's a small part of the industry we still have to do manual tests for engineering and bench tests. So for this setup, we have the PCB board, and then on top of it mount a socket. Within that socket, we have a preload probe that provide the electrical path between the PCB and the device during test. So once the device is placed inside the IC opening of the socket, we use a manual lead to actuate the device downward. and compress the probe to during test. So during test, the majority of the generated heat is dissipated to the top of the device. So for this presentation, we mainly focused on the lid part with the heatsink inside for the thermal management. Right. So we know that for device that is up to 200 to 250 watt, the traditional heatsink and fan cooling is sufficient, and is the a first choice to go due to cost. So the example here is a lid that we designed for a device that generates 200 watt. This lid right here. Let me see. So to dissipate 200 watt, the heatsink is very large. The size is around 74 by 74 by 50 millimeter copper block. And then we use a very strong fan to help dissipate it. So as you can see, 200 watt, the heatsink is big and the fan is loud. The noise level is around 74 decibel. With the air cool, in order to increase the dissipation, then either we get a larger heatsink or we increase the flow. The material choice, we do not have that much. Either we stick to the copper or the aluminum. So not much we can do. We focus on the size and the flow, improve the flow. So from 200 watt to 200 watt, 250 watt, you see the lid in the bottom. The size already increased by double. And then we also have to use the two fans to help dissipate the heat. So from here, we can see that the traditional cooling heatsink and fan is already reached the limit. It reached the limit. And then also the space limitation, because it is you see the 250 watt lid is around 2 to 3 times bigger than the device size. So this is not ideal for the PCB designer with the impedance matching. They want to place the component very close to the device as much as possible. So with this big size of lid is not ideal. And then also if we use the improve the flow, the fan level is very noisy. It is up to like greater than 60 decibel to 80 decibel. If you compare it to a quiet office, which is around only 50 decibel. So imagine the noise if you test it with the air cool heatsink fan. So recently there's a lot of interested in moving to using vapor chamber or heat pipe into the manual lid for testing. So for this one, we see that the vapor chamber is used to spread the heat. So we need this vapor chamber is not ideal for manual tests, especially if we need to design it to fit within this side of lid, as you see in the bottom. So the heat spreader is not ideal. The heat pipe, because it moves the heat to a remote heat sink, and then heat pipe, we can have the capability to bend. So most of the time we use heat pipe in the lid for the manual test. And below you can see the heat pipe heatsink that we designed for 300 watts. The simulation, we saw the result. The junction temperature is around 77 degrees C, but in the actual part, when we finish the assembly, we tested and it can dissipate 300 watts and keeping the junction temperature at around 65 degrees C. So this one is, the next one is
Quynh, sorry, Quynh, this question regarding,
sure.
if you could go back to your slide, the one before.
This one.
Yeah, so simulation, so I mean that, I assume that to mean model?
Yes.
Yes, so in this case, it turned out better, the actual turned out better in the model, right?
That's true.
So have you had cases though where it's the opposite, where the model's better in the measured? And do you adjust your model then for the next time to be able to predict more accurately?
All right. So we've seen case that the model is actually better than worse than the measurement, and we do adjust the parameter. But the parameter mostly we adjust. We do not have a lot of room to adjust. So the goal is that we want to have the simulation better than the measurement, worse than the measurement, so that we have some gap for assembly tolerance and all other tolerance build up during the heat pipe manufacturing.
Could I just answer just on top of that real quick?
Mm-hmm.
So yeah, we are newly developing heat pipes, and it is a relatively new product to market. So as we're able to validate and correlate more of our production heat pipe lids, our model is getting smarter and it's getting more accurate. But we are definitely undershooting in our simulation. And
so can I say, in other words, maybe you plug in worst case, so that way your actual will probably be better. Is that
Yes.
absolutely.
Yeah.
Okay.
Sorry.
That's the goal. We want the worst case all the time dealing with the model.
Okay. Thank you. Go ahead.
So this heatsink right here, we designed it to dissipate 600 watts. And as you can see, compared to the previous one that on the previous slide, the quantity of pipe also increased, and then the fan is doubled. Right here, the simulation is around 74 degrees C. And then when we measure the heatsink, it's around 58 degrees C. So this is a case temperature. The previous one is the junction temperature. So as you can see, if we compare it, the 600 watt heat pipe heatsink to the 250 watt traditional heatsink and fan, the size of the heatsink is the same, including the heat pipe heatsink is including the fan is the same size as the regular copper heatsink. So the benefit of the heat pipe is that because it bend, the pipe are bendable, so we can raise up the fin area, and then we can increase the surface of the fin area for dissipation. At the bottom, it have a smaller footprint area, so it allows the PCB designer to bring the component closer to the device for better impedance matching. And then also because we can raise up the fin area, we have more surface for fin, and then we also have a larger fan. With larger fan, then we can use bigger motor and then therefore the noise level will reduce. So it can be reduced better. We can use fan that is around 53 decibel. So it's better than the other one before, where we have like 74 or 80 decibel. So with the because it has better thermal capacity, heat pipe heatsink, it can dissipate up to 600 watt. If we manufacture it in high volume, the cost is low. But if we do it in the low volume, then the cost is high because there's cost involving with the tooling and then also with the assembly and testing. So another option to address the high power device testing is to use liquid cool. So in this list right here, you've seen this a liquid cool we designed that it can connect to the water line available in the lab facility. For this one, the simulation we have is for the 500 watt. And with that, the case temperature is around less than 85 degrees C. The fluid is from the water line, so you cannot change the temperature or you cannot change the flow. So for this example, it's around 0.75 gallon per minute. Now, for those lab facilities that do not have water line available, then this lid can be connected to a radiator for the liquid cool option. Also, another one is that the lid can also be installed here with the chiller. With the chiller, then we have an option to change the set point or control the set point so that it can improve the heating, the dissipating capability. If we it can set the ambient below, it can set the temperature below ambient. So for this example, the graph below, we set the chiller at 15 degrees C. And at 15 degrees C, we test the device at around 450 watts. The junction temperature is around 70 degrees C. So we can set the temperature, the set point to as low as 10 degrees C. When we set it to 10 degrees C, then we start seeing condensation. So we need to insulate the hose, and then we also need to introduce the purge into the lid. Right. It depends on the chiller. One chiller, we can have two lid connect to that chiller, but the chiller with the two lid, the total dissipation power of that two lid need to be at the lower than the capability of the chiller. So at the lid, water can transfer heat better than air. So therefore, liquid cool heatsink can dissipate to greater. I think around 500 to 600 or 700 watts. So it is, if we talk about the lid portion by itself, the cost is less than the heat pipe. the chiller is a one-time purchase, so it's not that expensive, and the maintenance is easier. The weight of the lid is also lighter than the traditional copper heatsink. And then if we use it in the with the water line in the lab, then there's no noise. But if we use it with the radiator or the chiller, the noise level is very low. The only thing is that if you use it with the water line in the lab or the radiator, then you cannot change the temperature, flow rate, you change the temperature of the fluid or the flow rate of the fluid. Therefore, if you need to manipulate the temperature and then use it with the chiller. But when you use liquid cool, we need to pay attention for the leakage. Another.
Can I just clarify one thing, Quynh?
Yes.
So just a little background on the first two slides. The heat pipe and liquid cooling actually fall under what we consider passive cooling and not an active cooling solution, which is what Quynh was referring to there, not being able to create a set point for your duct. So just a little point of clarity. Thank you.
Hey, Tim, so to kind of follow up on what you just said, so say, you know, you want the silicon to be at a certain temperature for, you know, during the test. So then you have to characterize what level, what set point to set your chiller, so that when during the test, the silicon gets to the desired set point.
We do. We actually work closely with our customers and are monitoring typically the thermal diode of the device and adjusting the chiller, in this case, in the previous slide, to the correct set point so that we can achieve their target result.
Right. And then there's a question from the audience. Does the liquid cooled heatsink have the options of a heater, making it a complete thermal solution?
It absolutely does. And it's something that we're starting to integrate more and more, is to be able to heat the device using a controller, as well as using in this case, this chiller for cooling.
So I think.
Sorry, Quynh, and then the last question in regards to this. Have these solutions been integrated into a handler?
We have not integrated the heating portion into the handler at this time, and we've not been requested to do so to date.
Okay, thank you. Go ahead, Quynh.
All right. So I think for the next part, we're talking about the temperature control unit. The heatsink that we said before, it can be connected to a fan or a water line or a chiller for cooling. And then at the same time, we can use it together with a controller so that we can control the temperature of the device during test. When we use with the controller, then we have a capability to test it at tri-temp, heating, cooling, or unpowered. So for the heating part, as you can see right here, we can use the TEC, or we can use the heater rod for the heating. And for the cooling, we connect it to either fan, chiller, or the water line. Is depend on the requirement. And then between the contact surface of the pedestal and the die surface, there is a resistant temperature detector mounted. That one it will detect the case temperature of the device, and then it will provide a feedback to the controller, and then the controller will manipulate to either turn on or off the heating, the TEC or the heater rod. The one you see right here that we have in this lid is it's connected to a liquid cool chiller. So the advantage is for this one is the same as the liquid cool that we discussed before, but then it have the capability for tri-temp cooling. And then it's also the maintenance and the setup is similar, but for this case, because we have the controller and the chiller, so it takes more space. If you have like a test floor configuration, you need to consider the space for all this add-on, as well as some of the host routing. Then recently, there are some immersion cooling that we see. Right now, most of the immersion cooling is used in data center or the crypto mining. But we also have a solution developed for the submerged cooling. What is the submerged cooling is that there's a enclosed enclosed test bath filled with the 3M Novit. I think it's the 7500, the engineering fluid. I think there are other fluid as well. And within this enclosed system, the fluid is it dissipate the heat using the vapor process. So it have a lower boiling point, and then when the heat is generated from the device, it will boil the fluid, and the vapor will go up to the condenser on the top to condense down into the fluid. The condenser on the top is have the facility water running through to help the condensing process. So I think I don't know if a lot of tests is for the device testing is gonna using immersion cool, but there are a small person of customer is using it right now. I think if we transfer a lot of people is resist to change to immersion because we have to do a lot of changing to the test setup that we have right now. And then if we are able to move to the immersion testing, then we have to save a lot of power energy for like the fan. And then also a lot of other hardware is gonna be reduced for the space. So this is the summary table I put up for the different cooling solution we have for the manual test. I think the lowest one is the heatsink air cool, but it only reach up to a certain around 250 watts. For the higher option, then we can go with the heat pipe or the liquid cool. It depends on the test requirement that you have. Maybe some lab have water, then you can use it. Otherwise, we can go with the heat pipe. So I think that part concludes the presentation. Thank you for your time.
Okay, Quinn, we have some other questions in the queue.
Sure.
So are there any new materials being researched for the heatsink? Yeah, I think you mentioned aluminum, copper. So any other materials to help improve the thermal cooling?
I think there are research for other material, but then the cost may be high. Right now, we are focusing to control the cost. So unless there are a high demand for it, the cost cannot be drive down.
Okay. And then which TIM solutions will be used for the heatsink design shown, considering the reusability of the duct?
For the most of the design that we have two type of TIM that we use. One is from Indium, right, Tim? And
Yep.
then the other one is from Fuji Poly.
Okay.
See, I just realized the hard part about doing a thermal presentation when your name's Tim is that I don't know if she's talking to me or if she's referring to India. Sorry, didn't mean to distract the question.
No, hey, that's fine. And then regarding boiling, since the bubbles increase the interfacial thermal resistance, is this a problem? Or is this a concern? How do you address it if it is?
This is in the bath
In the back.
scenario.
Mm-hmm.
You know, we don't have a tremendous amount of experience in the bath setups yet. We're starting to see it be more implemented across a wider network of our customer base, just due to their device requirements. And as we're learning more of these different options, you know, we're seeing all types of challenges. I think that's the bubbles are an area we've talked about, but don't have a tremendous understanding of the effect of the boiling point yet. So I'm sorry I don't have a clear answer on that one.
Okay. I think we've come to the end of Quynh and Tim's presentation. Thank you so much.
I also want to thank our sponsors once again for making this event possible: Advantest, Amcor, Indium, Form Factor, and Nidec SVTCL. Advantest is a global leader in the ATE industry with over 30,000 installed systems using nanotechnology products to support leading edge process nodes with a large global workforce over 50 countries, working in environmentally sound processes. Amcor, who's providing OSAT services with a focus on technology, quality, and service, certainly advanced packaging, quality first, and service from design and test through drop ship, using a global footprint from around the world, but with local sales and support. And Indium, the premier assembly materials designer and manufacturer of thermal interface materials, solder paste fluxes and preforms, and certainly metals and compounds to solve challenging thermal problems. So once again, I'd like to thank all the sponsors. When you have an opportunity, please thank them yourselves to encourage them to sponsor more great events like Too Hot to Test. And so thank you very much for joining us, and I wish you a good rest of your day and look forward to having you participate at a future MEPTEC event. Thank you.